Hello students and welcome to the lecture. So students, as we know that we are covering the light and so far we have completed till part 5. This is going to be our light part 6. I hope that you have revised the previous parts in the well enough manner before you have come for this part. As many times I have reminded you, it is for your own benefit. So if you are doing this on the regular basis, the thing will be good for you. If not, then you may face some struggle while compiling the things that you had learned before the examination. Okay. So in this lecture, basically we are going to talk about the defects of image, rainbow, primary, secondary and complementary colors, scattering of light, blue color of sky and ocean, interference, conditions for observing sustained interference with port contrast, illustration of interference, applications of interference, diffraction, types of diffraction of light, interference and diffraction, points of difference, polarization, some important facts about polarization. So these all are going to be the topics for our discussion in this particular lecture, starting with the defects of image, then rainbow, primary, secondary and complementary colors, scattering of light, blue color of sky and ocean, interference, conditions for observing sustained interference with port contrast, illustration of interference, application of interference, diffraction, types of diffraction of light, interference and diffraction, points of difference, polarization, some important facts about polarization. But before starting the actual discussion, as usual, we have the small disclaimer over here that we are required to understood before we proceed further. The disclaimer goes like, the images used in a slide deck are for educational purposes only. We respect the intellectual property rights of the original creators and owners of these images. If you are the owner of any of the images used in this deck and have any concerns or issues, please contact us at sathee@iitk.ac.in and we shall remove the images. Now, let's begin with the defects of image. The simple theory of image formation developed for mirrors and lenses suffers from various approximations. As a result, actual image formed by an optical system is usually imperfect, that is not the perfect image. The imperfection or defects of image are called aberrations, which arise either due to light or optical system. If the defect in image is due to light, it is called chromatic aberration, and if due to optical system, monochromatic aberration. Monochromatic aberration is of many types such as spherical coma, distortion, curvature and astigmatism. So now if we talk about the defects of image, first we have to talk about the theory of image formation. So simply if we go by this theory, we could say that the formation of image for various kind of mirrors and lenses is actually going through or suffers from various approximation. Because of this various approximation, usually the image that is formed is imperfect. It is not the perfect image. You can't say that the thing that we observe is exactly the reflecting thing. No, that will not happen. There will be some imperfection. And these imperfection or defects of images actually having some causes, and we call them as aberrations, the imperfections or defects of image. And this cause could be either light or optical system. Any of them could give a rise or could cause these aberration. There is nothing a hard and fast rule, then only light or only the optical system will do it. Any of them could do it. So if the defect appears because of the light, it is what we call as a chromatic aberration. If it appears because of the optical system, we call it as a monochromatic aberration. And this monochromatic aberration could be of many types: spherical, coma, distortion, curvature, and astigmatism. Okay. After the defect of light, defect of image, now let's have a look over the rainbow. Now, rainbow is the thing that we all have seen. Okay, in your childhood, even in today, you could see the rainbow. It generally appears after the rain when the sun shines, arrives. Okay, then we could see a phenomenon of rainbow. Here, we are not going to talk about like there is a rainbow. We are going to talk about what is the process behind formation of rainbow and what is the association with light of this particular phenomenon. So here we could say when sunlight falls on small water droplets that are suspended in air during or after a rain, it suffers refraction, internal reflection and dispersion. So basically what happens whenever the rain arrives during that time and when the rain just stops during this time also, there will be some droplets, water droplets in the air that are suspended. And these are actually work as a reflector. So when the sunlight falls on them, actually the sunlight goes through refraction because the medium is changes, internal reflection and also the dispersion. So all these three, refraction, internal reflection and dispersion, all these three actually give rise to the rainbow. If an observer has the sun at the back and the water droplet in front, we may see two rainbows, one inside the other. Like here you can see. If you are standing here and the sun is beside you, maybe here, then you will see two rainbows, one rainbow in another. Okay? The inner one is called the primary rainbow and the other one is called the secondary rainbow. Here in this picture you can see this is the secondary rainbow, the outer, this is the primary rainbow inner, and here you can see there is two rainbow, one in another. Figure shows the path of a typical ray forming the primary bow. It suffers a refraction followed by an internal reflection and then again a refraction. So first the refraction happens, second internal reflection happens, again refraction happens when the primary bow is to be prepared or is to be appeared. The condition, remember, to see the two rainbows at a given time is that the sun must be at your back and water droplets must be in front of you. Then you see the two rainbows in front of you and it usually appears like one rainbow is coming out of another. The inner one is called the primary and the outer one is called the secondary. For inner one, first the refraction happens, then internal reflection happens and again the refraction will happen. Dispersion takes place at both the refraction. In a primary rainbow, the arc shows red on the outer part and violet on the inner side. For the red color, the maximum deviation is 137.8 degree, so that the angle theta in figure is 180 minus 137.8 degree equals to 42.2 degree. For the violet, this angle is 40.6 degree and for other colors it is in between 40.6 degree and 42.2 degree. Therefore, red rays coming to the observer will appear to come from circle which subtends an angle of 42.2 degree on the eye. Similarly, the violet rays coming to the observer will appear to come from a circle which subtends an angle of 40.6 degree on the eye. So we could say basically whenever we seeing a primary rainbow, it usually shows that the violet is in the inner side and the red is on the outer part. So here you can say this is the red part, this is the violet. Okay. Why it is happening? Because for red, the angle of deviation after going to the theta nearly about 42.2 degree and for violet it is 40.6 degree. For other colors it is nearly about 40.6 degree to 42.2 degree. That's why this is the violet, this is the red and all others are fall between them. So we see the violet in the inner side, the red on the outer and other colors in midway of these. Got it? From the ground level, only an arc of rainbow is usually visible. A complete circular rainbow may be seen from an elevated position such as from an aeroplane. Like you can say only you see this arc from the ground. If you are standing on the ground, you can only see. But if you are at some kind of elevated area, for example, an aeroplane, then you will see a complete circular rainbow. The secondary rainbow is formed by rays which suffer two internal reflections before coming out of the water droplets. Like for the primary, only the reflection, internal reflection, and then the reflection. And dispersion will happen at both times of the reflection, first and last. But for secondary, actually, the rays go through two times of internal reflections before they come out of the water drops. In this, the order of color got reversed. Red appears on the inner circle in the rainbow and violet on the outer. The angle theta is 50.5 degree for red and 54 for violet. Note, secondary rainbow is less intense than primary rainbow. So here you can see it. This is the primary rainbow. The red is at outer and violet is in inner. In the secondary rainbow, this case is got reverse. The violet is at outer and red is in inner. Okay, because here the angle theta got reverse for red and for violet. For red, it becomes lower, 50.5 degree, and for violet, it becomes 54 degree higher. Okay, but remember, if we go by the intensity, the secondary rainbow is always less intense than the primary rainbow. Now, the primary, secondary, and complementary colors. First, primary colors. The spectral colors, blue, green, and red, they are called the primary colors because all these colors could be produced by mixing these in proper proportion. So we could say the basic primary or the fundamental, you can say, colors are blue, green, and red. Okay, and all the colors could be produced by mixing them together, but in a proper proportion. Blue plus red plus green becomes white. Secondary colors. The color produced by mixing any two primary colors is called a secondary color. There are three secondary colors, yellow, magenta, and cyan, as green plus red, yellow, red plus blue, magenta, blue plus green, cyan. So here you can say primary colors are those colors which not to be mixed and not to be prepared by mixing. They are present as fundamental, like blue, red, and green. Okay, and secondary colors are those colors which could be produced by mixing any two primary colors. For example, yellow, magenta, and cyan. For yellow, we mix the primary colors of green and red. For magenta, we mix the primary colors of red and blue. For cyan, we mixed primary colors of blue and green. Okay. When the three secondary colors are mixed, white color is produced. Yellow plus magenta plus cyan equals to white. We know yellow plus magenta and cyan, these are not the primary colors, these are secondary colors. Now, what are the complementary colors? So, any two colors when added produce white light are said to be complementary colors. Clearly, a secondary color and the remaining primary color are complementary colors because whenever they got mixed, they always produce a white light. Red and cyan, blue and green and magenta, these are complementary of each other's. The different colors and their mixtures are shown by the color triangle. Note, in color television, the primary colors, therefore red, green, and blue are used, and these are mixed together in a proper proportion to produce the other rest of the colors. Now, what are the color of bodies? So the color of a body is the color of light which it reflects or transmits. An object is white if it reflects all the components of white light, and it is black if it absorbs all the light incident over it. This is why a red rose appears red when viewed in white or red light but appears black when viewed in blue or green light. So here we could say, like if we talk about what is the color of body, then the color of body is actually got determined by the fact of reflection of light or transmit of light. For example, just look around yourself. If you are seeing any black object, it is appearing black. Why? Because it absorbing all the light that is falling on it. It is not reflecting or transmitting any light back to you. That's why it is appearing totally black. If there is anything nearby you which is white, it is appearing white. Why? Because it is reflecting or transmitting all the components of white light. Similarly, if there is something that is appear green to you, it is because it is only able to reflecting the green color back to you. So that's why it's appear green to you. So here you could say there is a finest example that we have here. If you see a red rose, whenever you take it out, you always see it as a red. Why? Because it is transmitting or reflecting the red light back to you. That's why it appears as a red. So when you see the red rose in the white or red light, it appears red. But if you take it to the blue and green light and then you try to see it, it won't be able to reflect the light back to you. So it appears black on that time. So the color of a body is actually getting determined by the reflecting or transmitting color of light. That is, it is reflecting or transmitting back to you. Now the primary, secondary and complementary colors. Here again we have how a body will appear in light of different colors could be understood by the following table. So here we have a table to understand that how the one object will appear different in different colors. So name of object in white light, in red light, in green light, in yellow light and in blue light. First, let's talk about the white paper. In white light, it appears white. In red light, it appears red. Green light, it appears green. Yellow light, it appears yellow. And blue light, it appears blue. For red paper, in white light, appears red. In red light, appears red. In green light, blaze. In yellow light, black. In blue light, black. For green paper, in white light, green. In red light, black. In green light, black. Sorry, in green light, green, not black. In yellow light, black. In blue light, black. Yellow paper, in white light, yellow. In red light, black. In green light, black. In yellow light, yellow. In blue light, black. For blue paper, in white light, blue. In red light, blue. In green light, black. In yellow light, black. In blue light, blue. So here you can say for different cases we have the same object. White paper, red paper, green paper, yellow paper, blue paper. But here you can say their appearance got changed when they got exposed to the different lights. For white light, they have the different appearance. For red light, different. For green light, different. For yellow light, different. For blue light, different. Because of the reflection and the transmission that they are doing on that time when they are exposed to the different lights. Then we have the scattering of light. So what do we mean by the scattering of light and how it affects the appearance of things to us? So the process in which radiation is deflected by the particles in the medium through which radiation passes is called scattering of light. For example, if this is the particles suspended in a medium and this is the ray of light, when it's come, it actually got scattered here and there. So this scattering is actually what we call as a scattering of light. It is happened because of the particles that are present in the medium through which the radiation is going through. Laws of scattering were quantitatively studied by Lord Rayleigh, John Tyndall, C.V. Raman and others. According to Rayleigh's scattering formula, the intensity of scattered light is proportional to the fourth power of the wavelength of the incident light, provided the diameters of the scattering particles are smaller than the wavelength of light. Therefore, I is inversely proportional to 1 by lambda 4. Thus, scattered intensity is maximum for shorter wavelengths. Rayleigh scattering is called coherent scattering because the scattered light contains only the incident wavelength. So we could say the shorter the wavelength, the more the intensity. The longer the wavelength, the less will be the intensity. For what? For scattering. Okay. And remember, Rayleigh scattering is also what we called as the coherent scattering. Why? Because it contains only the incident wavelength. Now, what is the reason behind the blue color of sky and ocean? Why they appear blue? So blue color of sky is due to the scattering of sunlight by the molecules of air. According to Rayleigh scattering law, I is inversely proportional to 1 by lambda 4. So the intensity of scattered light is maximum for the shortest wavelength, violet. The scattered light contains violet, blue and green. Out of this, violet is again scattered and it's removed. Indigo is not much sensitive to our eye and it is in less amount. So what we see is blue color which has maximum intensity. So generally what happens when the sun rays enter the earth atmosphere, and we know the earth atmosphere is not a vacuum, it's actually containing a different layers of air. Because of this, there are so many particles or what we call as the molecules of air suspended in the earth atmosphere. So when the sunlight strikes on them, actually the scattering of light happens with violet, blue and green. But what happened in that time? We could only see the blue. Why? Because the blue having a maximum intensity. So that's why it appears blue. So whenever you look at the sky, at the sky during the clear day, you will always find it in a blue color because the scattering of light of blue color with the maximum intensity. If there was no atmosphere, the sky would look perfectly black on that time. Clouds are white because the size of the particles scattering light is larger than the wavelength of the incident light. So that's why the incident light is not get divided into the division. It appears to be one incident ray. So because the white light is falling on the clouds and the entire light is reflected back. So that's why the clouds appears white. These particles cause diffuse reflection. So clouds look white. Blue color of ocean is due to the scattering of light by water molecules. And at that time also, the blue color having a maximum intensity. So that's why they appear blue. Now here you can say the skies appear black. Why? Because there is no atmosphere, no suspended particles. So that's why the scattering of light phenomena is not observing here. That's why it appears perfectly black. Red color during the sunrise and sunset. So during the sunrise and sunset, light has to travel a greater distance. So shorter wavelengths are scattered and removed. What we see is sunlight minus scattered light, which is red in color. The smoke from a cigarette, the grayish color of many minerals, etc. are also due to the scattering of light. Now, what do you mean by the interference? So the distribution of energy in medium due to a single source is uniform. But if there are two sources of light having the same wavelength, frequency, amplitude and same phase, or even with a constant phase difference, then the distribution of energy is actually not uniform due to the superposition of the two waves. This modification in the distribution of light energy due to the superposition of two or more waves is what we call as interference. At points where the crest of one wave falls upon the crest of the outer or other, or trough of one falls upon the trough of the second wave, the resultant amplitude is the sum of the two. Hence, the intensity is maximum. This is called the constructive interference. Here you can see it. There are the two different rays got combined, and now you can say they have appeared as a one ray only. At some other points where the crest of one wave falls upon the trough of the other, the resultant amplitude is the difference of the two. Hence, the intensity is minimum or zero if two amplitudes are equal. This is called destructive interference. The phenomenon of interference is shown by both longitudinal and transverse waves. Therefore, we could show interference with sound waves, electromagnetic waves, and water waves. Why? Because sound waves are mechanical longitudinal waves, whereas the electromagnetic are transverse waves, and even we could see it with the water waves. Now, what are the conditions for observing the sustained interference with pood contrast? For sustained interference, the first requirement is that we need a pair of coherent sources. There is a note. Coherent sources are a pair of sources which emits light of same wavelength, same frequency, and equal intensity or amplitude in the same direction. The two light waves must be in the same phase or with a constant initial phase difference. The light emitted by the two sources must be in the same state of polarization. Therefore, the light energy emitted by the two sources must be confined to the same plane. Then only we could go with the coherent source of light. In general, coherent sources are produced from a single monochromatic source. Here you can see this one. The beam emitted from the source is maniated into two by refraction or reflection or by using the slits. The initial phase between the interfering waves must remain constant, otherwise the interference will not be sustained. The frequencies and wavelength of the two waves should be equal. If frequencies and wavelength not equal, the phase difference will not remain constant, and so as the interference will not be sustained. The light must be monochromatic, another condition. This eliminates overlapping of patterns as each wavelength corresponds to one interference pattern. The amplitudes of the interfering waves must be equal. Thus, this improves contrast with I max equals to 4I0 and I minimum equals to 0. The source must be close to each other, otherwise due to the small fringe, width fringes may be so close to each other that the eye cannot resolve them, the resulting uniform illumination. The source must be narrow. A broad source will be equal to a large number of narrow sources, and each set of two sources will give its own pattern, and overlapping of patterns will result in uniform illumination. If the interfering beams are polarized, they must be in the same state of polarization. Otherwise, instead of interference, unpolarized light will result. Now, what are the illustrations of interference? Interference effects are commonly observed in thin films when their thickness is comparable to wavelength of incident light. Thin layer of oil on water surface and soap bubbles show varied colors in white light due to the interference of waves reflected from the two sources of the film. The brilliant colors we see in the inner surface of an oyster shell and peacock feather are also due to the interference of light. The multi-layer structure causes constructive interference for certain colors such as blues and greens. The color changes with change in direction of view. Now, what are the applications of interference? The phenomenon of interference having a wide range of applications. It has been used to calibrate the standard meter in terms of wavelength of light. It has been used as Michelson and Morley in their famous experiment which disproved the existence of ether. It is used in holography to produce three-dimensional images also. It is used to test the flatness and parallelism of plane surfaces. So we could use them here. First, calibrate the standard meter in terms of wavelength of light. Second, it is also used by Michelson and Morley for their famous experiment which they did to disprove the existence of ether. It is also used in holography to produce the three-dimensional images by using the interference of light. It is used to test the flatness and parallelism of plane surfaces, like how plane the surface is and how parallel it is. It is also used to minimize the reflective losses in lenses and solar cells by coating them with thin films of MgF2 and SiO respectively. It is used to determine the wavelengths of light lambda precisely. It is used to design optical filter which passes a narrow band of wavelength of light of width up to 100 angstrom. It is used to determine refractive index or thickness of transparent thin sheets. Now let's have a talk over the diffraction. So the phenomenon of bending of light round the sharp corners and spreading into the regions of geometrical shadow is called diffraction. It is discovered by Grimaldi, who is in Italy in the 17th century. The light waves are actually diffracted only when the size of the obstacle is comparable to the wavelength of the light, and in most of the cases, narrow sources emitting the monochromatic light required to see the diffraction. Diffraction effect observed with silt, a pinhole, a wire, or edges of razor blade, etc. In principle, all types of wave motion exhibits the diffraction effect. Now, what are the types of diffraction of light? First is Fresnel diffraction. So it is the type of diffraction that actually take place at a slit when the source of light lies a finite distance from it. Second one is Fraunhofer diffraction. It is the type of diffraction that take place at a slit when a plane wavefront is incident on it and the wavefront emerging from the slit is also plane. Obviously, we could say both the source and the screen should be at infinite distance from the narrow slit. There is a note. Fresnel gave the exact explanation of the phenomenon of diffraction. According to him, diffraction is due to the interference of secondary wavelets that are originating from the portion of the primary wavefront, which is not blocked by the slit or the obstacle. Now, interference and diffraction, what are the points of difference? Let's have a talk over them. So following are the main points of difference between the interference and the diffraction. For interference is the result of interaction of light that is coming from two different wavefronts originating from two coherent sources, whereas diffraction pattern is the result of interaction of light coming from different patterns of same wavefront. In interference, the fringes may or may not be of the same width, while in diffraction, the fringes are always of varying width. So in interference, it could be same, it could not be same. But for diffraction, it always different or varying. In interference, the fringes of minimum intensity are perfectly dark, provided light waves are of same amplitude, whereas in diffraction, the fringes of minimum intensity are not perfectly dark. In interference, all the bright fringes are of same intensity, while in diffraction, the bright fringes are of varying intensity. In the interference pattern, there is a good contrast between the bright and dark fringes. On the other hand, in diffraction pattern, the contrast between the bright and dark fringes is comparatively poor. Now, let's have a discussion over the polarization. The phenomenon due to which the vibrations of light are restricted in a particular plane is what we call the polarization of light. According to the electromagnetic theory of light, a light wave consists of electric and magnetic vectors vibrating in mutually perpendicular planes. Both are perpendicular to the direction of propagation of light. The electric vector acts like a light vector. Hence, the plane polarized light is a light in which the light vector vibrates along fixed straight line in a plane that is perpendicular to the direction of propagation. Now here you can say symbolic representation. This is the unpolarized light. This is the plane polarized light. This is the plane polarized light with vibrations in the plane of paper. This is plane polarized light with the vibration perpendicular to the plane of paper. Some important facts about polarization. If an unpolarized light is converted into plane polarized light, its intensity reduced to half. Polarization is a convincing proof of transverse nature of wave, as in a transverse waves vibration are in a plane perpendicular to the direction of wave motion, and so the wave could be polarized. However, if the wave is longitudinal, therefore vibrations in a wave are along the direction of wave motion, it couldn't be polarized. This is why light could be polarized while sound couldn't be. So with this, we have finished this part also. It is requested again to all of you, kindly revise the facts and figures that all we discuss in this lecture and keep yourself ready for the another lecture. With this note, let's end this lecture and thank you.